Well, good morning. I'm Bill Kresnor, and this is Brandon Mueller, and we are William R. Kresnor and Associates, a soil and environmental consulting firm located in Woodstock. Been in business almost 35 years now. What we do is we collect soil samples, do soil sampling in order to provide information to our clients to make sure that the land use that is planned for a site is appropriate for the soil conditions. The drilling rig here allows us to collect a relatively undisturbed core sample for examination. And we have the ability to pull core diameters anywhere from 1 inch to 3 inches in diameter. We also can do some augering in the event we have to do some deeper exploration. So what we have here is the more gravelly material in the lower part of the soil, and it's overlain with a siltier or loamy material. It's got more clay, less sand, certainly not the amount of rocks. And part of it has to do with the volume of water. When the ice sheet melted, at times there was a tremendous volume, so it could carry relatively heavy material like rocks like this, and there's actually, I did some borings over at the Menards over in Crystal Lake, and there's some huge boulders down there that were brought in by water. So you can imagine how much water, the power of that water to move boulders, half the size of me. So this is a very common soil in this area. It's called either a Wapikon soil or a Bose. It depends on the thickness of the surface layer, but as you can see, it's very kind of straightforward, nice brown, not a lot of variation in terms of the color in the subsoil. The surface is pretty uniform anyway. So again, just for your own information, that's kind of what you've got in the campus area around here. So it's a very productive, very well-drained soil. I mean, I think it's relatively easily managed. The gravel's deep enough so that there's not a problem with any kind of water holding capacity. It's got pretty good available water holding capacity, and it doesn't get real droughty. So what I have here are two soil types that are relatively common in the state of Illinois. We classify soils much like we classify plants and animals. It's a kind of a hierarchical classification. We have what we call soil orders. There are 12 of those worldwide. And that is the highest level of classification. And then the soil series, or what we call the soil type or soil name, would be the lowest level of classification. So Illinois is known as the prairie state, but actually if you were to tabulate the acreage of prairie soils versus forest soils, you'd find that actually there are more forest soils in the state of Illinois than prairie soils. Well, they're very close. I think it's like 45% forest soils, 43% prairie soils. As soil scientists, soil classifiers, we have names for our soils. The two soil orders that are most predominant in Illinois are the mollisol, which is a prairie soil, and the alpha soil, which is a forest soil. And there are some striking differences between the two. One reason we classify soils, and why we classify anything really, is that it allows us to group things that will act the same in terms of their properties together, and then separate soils that are radically different from each other. And there's a geographic component to that classification in that we can use our knowledge of how soils form and develop and actually map those soils in the landscape. And that's very important in terms of land use planning. If we know what the soil conditions are on the ground, then we can plan the appropriate use and management of those soils. So these two soils, as I was saying, are the dominant soils in the state of Illinois, the mollisol, which is prairie soil, and alpha soil, the forest soil. And one of the major differences between the two is the thickness of the surface layer, or what we would call the A horizon. In soil terminology, we describe the layers as horizons. And if you think about the alphabet, we describe A horizon, which is typically a surface layer, B horizon, which is a subsoil, and C horizon, which is the underlying material, or sometimes known as the parent material. So if we look at, get some nails here. If we look at the A horizon, or the surface layer, in the alpha soil, the forest soil, it's relatively thin. The A horizon in the prairie soil is much thicker. It has to do with the amount of organic carbon, organic matter in the soil. If you think about where the organic matter is in a forest, most of it is above ground, right? In the trees, the leaves, the branches, the stem of the tree, and so forth. In a prairie environment, most of the organic matter is in the roots of the grasses. So that is why prairie soils are darker, and the surface layer is darker and thicker than what we find in a forest soil. So below our A horizon, in the forest soil, we have what we call an E horizon. The E horizon tends to be kind of an ashy or gray in color, and the reason why it is that way is because in a forest environment, you get what we call acid leaching, the decomposition of the various leaves. As the wetting fronts move through the soil, a lot of the organic matter is dissolved, or it goes into suspension along with the clay, and it's moved from this layer into the underlying subsoil. In a forest or a prairie environment, we really don't have that kind of an acid leaching condition. So we don't get an E horizon. We get typically it goes from an A horizon to a B horizon, or what we call, commonly known as a subsoil layer. Another thing you'll notice quite a different about these soils is when we look at the subsoil is the coloration. The forest soil example here has a very brown subsoil, whereas the subsoil color in our prairie soil here is quite gray. And that has to do with the wetness of the soil, or what we call a seasonal high groundwater table. If you think about tools or such that you might leave in your yard after a rain, they become rusty. What happens is the iron in those tools oxidizes, and the same kind of processes occur in the soil. We call those features that are developed as a result of wetting and drying redoxomorphic features. Redox being reduction, oxidation. If you remember your high school or college chemistry classes, talk about loss of electrons is oxidation, gain of electrons is reduction. Well, the same processes are taking place in the soil. If the soil is rusty or nice and brown like this, it means that it's not very wet. Even after a significant rain, water will continue to move through it and won't build up. We won't have what we call a seasonal high groundwater table developing in these soils. When the soil is more wet, that iron in the soil, and iron is a very common element in all the soils of the world, that iron goes into a reduced state or becomes gray. So we use color as a very good indicator to tell us just how wet a soil is. And a simple way to think about it is brown, rusty is generally good, gray reduced, generally poor because of its wet. So say if you were going to build a house with a basement, you'd probably want a soil that looks more like this so that your sump pump wouldn't be running continuously as it would in a case like this where that seasonal saturation level here is probably at or near the soil surface. And here there's no evidence of any kind of saturation at all. Typically your surface layers, if you look at the soil structure, how the soil aggregates, typically your prairie soils, you'll see a more granular structure. Sometimes it'll be a little blocky as well, but typically it's a lot more granular. Same with the forest soil. Surface typically is granular. And then when we get into the subsoil, it becomes more blocky or even prismatic in some places. And as a result of freezing and thawing, plant roots, water moving through the soils tend to aggregate into these structural units. Here's a pretty good example of what we call a prism. The axis of the soil, it's got a long vertical axis and a shorter horizontal axis. So this is a structure we would call prismatic versus, say, a structure like this, which is more blocky. Structure is very important in terms of allowing roots to move through the soil, allowing water to move through the soil. Animal activity influences structure as well. Below our subsoil is what we would call our sea horizon. Sometimes it's known as parent material, sometimes underlying material. When we say parent material, we mean the material from which the soil forms. In some cases, we have multiple parent materials in the soil. For instance, in this area here, we have some glacial outwash, but it's overlain by a windblown sediment that we call loess. It's a very silty material. So that kind of a soil actually formed in two different parent materials. One thing you can note about in some soils, to get an idea of just how deeply they are developed or how deeply the wetting fronts move through the soil, is we can test for the presence of calcium carbonate in the soil. So what I'm doing is I'm applying some hydrochloric acid to what would be the sea horizon or the parent material of this particular soil. And if there's any calcium carbonate in it, it should kind of bubble and foam. It kind of gives a new meaning to dropping acid, I guess. But we're getting a bit of a reaction with the calcium carbonate. What happens is the hydrochloric acid reacts with the calcium carbonate in the soil and it generates carbon dioxide gas. That's what you see bubbling up there. But this is another way of seeing just how deeply the soil profile has developed or weathered, because the calcium carbonate is very soluble, and so as the wetting fronts move through the soil, it will dissolve the calcium carbonate, and then when those wetting fronts disperse or dry up, the calcium carbonate reprecipitates. So it gives, again, it's just another indication of perhaps how deeply the soil is developed or how old the soil is.
So I'm going to talk to you guys a little bit about soil health. Soil health is the capacity of a soil to function as a living organism. When looking at a healthy soil, we assess a few qualities and properties related to soils, and that would be chemical properties, physical properties, and biological properties. When we're dealing with the physical properties, we're looking at things like the good infiltration. So if there's any crusting on the surface, or if there's a low amount of compaction, so any kind of mechanical activity, whether it be any kind of vehicle or a tractor. And then we're also looking at how deep the soil is developed, as well as if it has good tilth or the consistency of it, if it can break apart easily. And then for the chemical aspect, we usually look at things like pH, the base saturation, and we're looking for a pH usually in the range of 6 to 7 for a good healthy soil, because that's when most of your macronutrients are going to be most available for the plants, and that's also when your heavy metals are going to be least available. And then for the biological aspect, we're looking again at the number of macro and microorganisms in the soil and earthworm channels. When it comes to protecting the soil, there are a few key things that a farmer or any kind of land manager can do. When I was in college, my professor always had 3 key rules to having a healthy soil. It was to never keep the soil bare, better alive than dead, which means better to plant a cover crop or some kind of crop that would cover the soil rather than just having residue on the surface. And then always add inputs of organic matter. Other activities that you could do is conservation tillage, so disking instead of deep moorboard plowing, no-till systems, which we're finding more and more farmers are adopting and are working for them. Definitely doing a rotation with your crops and not planting the same monocultural corn or bean product every year. Planting cover crops, and then there's also an idea of polycultural agriculture, which combines multiple crops on one single piece of land. Reducing the pesticide use, and as well as reducing or using efficiently as possible fertilizer applications. And I guess the last thing I was going to talk about, what are the key benefits of a healthy soil? So enhanced organic matter and organisms improve soil structure, aeration, water retention, drainage, and nutrient availability for plant growth. Reduced tillage and efficient fertilizer use also reduces expenses. And increased soil cover year-round sequesters more atmospheric carbon, which leads to higher air quality and more wildlife/plant diversity. So in the end, a healthy soil increases plant productivity while simultaneously reducing your costs. So the first thing we look at when kind of assessing soil health this way is see how easy it was to push the shovel into the ground. So we're looking for things like compaction from whether it be a tractor or again any kind of vehicle. And then once you do that kind of test, you're kind of trying to look at the consistency of the soil, how easily it breaks apart. And as you can see here, even though I kind of smeared it with the shovel, you can still grab chunks. And it comes off relatively easy. And then once it's in an aggregate like that, it really breaks apart easy. So that's usually a good indicator of a healthy soil. The next thing we're going to look for is things like these guys. That earthworm right there, which looks like it's building a channel, which is another important part of a healthy soil for porosity and water movement and air movement sake. And then the last thing you can do is give the soil a good smell. It smells great. If it has an earthy, kind of sweet smell to it, that's usually a good sign. But if you're smelling something that's more metallic-y or like a rotten egg odor, that's usually an indication of contamination. Did I forget anything?
Talking about structure?
Oh yeah, the roots too. So in a good healthy topsoil, the structure that we like to see break off a piece is something that's a little bit blocky that turns into granular. Granular structure is usually the structure you should see in a topsoil, and this definitely has that. Breaks apart really easily. And then the last thing I guess you're looking for is how well the roots go down into the soil. Here they look like they're going down straight, pretty much was what you're looking for in a healthy soil. You don't want them to have any bends because that usually indicates a root limiting layer. And then you can also see the different depths of the roots. And in a prairie system like this, you're kind of expecting a lot more diversity as far as plant species goes. So you should be able to see different rooting depths, and if you dig down even deeper, that would become more apparent. I think it would be a pretty good area for a farm or any kind of agriculture project.
That's excellent.